Right. Good evening, Doctor. I am Sosi Joel Ariko. I'm going to present you the models that I trained. So, contents of these presentations are as follows, as you're seeing them there. So, without wasting time, the introduction. So, I trained the two deep learning models that detected Babesia parasites from the microscopic blood smears. So the dataset, of course, contained of the four classes, which is Babesia, Plasmodium, red blood cells, and the leukocytes. So I used the two convolutional neural network models that I trained with efficient net B4 and ResNet 50. So these models were trained using transfer learning from the ImageNet. Then, of course, the objective was to compare the performances between them and see which one detects parasites the most perfectly. Then the architecture one was via the EfficientNet B4, which uses compound scaling to balance because there we have the network depth, we also have the network width and the image resolution. So for this particularly, I use the image resolution of 380 by 380, which is designed for efficient high performance deep learning. Then for the ResNet, of course, it's the deep convolutional neural network, which has 50 layers, as you're seeing here in this architecture. Both these architectures have different layers. Actually, they have multiple layers. So when you input images go through each of these layers until they form what we call a fully connected layer, where the predicted classes are formed. For example, we have Babesia, the leukocyte, the plasmodium, and the red blood cells. Yeah. So the ResNet prevents vanishing radon problem. Of course, the input resolution that I put, it was a 224 by 224, unless for the EfficientNet, which I used 380 by 380. So that is the visualization of the architecture for each, where you input images, they pass through different layers until they form what we call a fully connected layer, which helps to predict class probabilities. So how the models work, of course, you import images. For example, for both of them actually, you have to import images. Then, particularly for the EfficientNet BO4, you input the images through the convolutional layers. Of course, these layers that you're seeing. Then the feature maps are extracted to the multiple depths. Then we use the squeeze and excitation models to emphasize important feature channels. Then we globalize average polling aggregate features. Then finally, we form what we call a final fully connected layer that predicts class probabilities, as you're seeing there in that architecture. So same to the ResNet. Then how are these models learn? So both models learn using the supervised deep learning. Of course, the learning processes is you feed in the images, the model extracts the hierarchy features, but based on the hierarchy, then the model predicts these class probabilities. The prediction also compares with the true labels. Remember, it's based on label data. Then we also have the error calculated using the focal loss. Actually, a focal loss is a modification of the standard cross entropy loss designed to focus on hard examples and downweight easy examples. So therefore, since my data set had class imbalance. So I had to use Focal laws because it's best for classes that are actually that phase that problem of imbalance, actually imbalance in the data set. So I used Focal laws for that because it also reduces overfitting to easy examples. Then the optimizer that I used, it was what we call the ADAM W optimizer. ADAM actually is adaptive learning rate optimizer. Then the W stands for the weight decay regularization. So therefore, for why I actually chose it, it's because it updates the model's weights in order to minimize the loss function. And also it determines, of course, how much the model parameters should change after each batch of the data. So without this optimizer, it will be hard for the network to learn. Then also the weights would never update. So the advantages of the ADAM W optimizer, it's one, adaptive learning rates, then the weight decay regularization, then improved convergence stability also. Then additionally, had optimization techniques, for example, the cosine annealing learning rates scheduler. Actually, this is a strategy that is used to adjust the learning rate during training so that it gradually increases and then maybe probably increases in a smooth cosine shape curve. It helps also models to converge and often escape the sharp minima. So here we can have like the high learning rate at the start. Because this allows what models to explore the parameter space. Then we can have the lower learning rate later, allowing the fine-tuning weights more precisely. Then we have what we call the mixed precision training. This is a technique where computations use both half precision and full precision floating point numbers during, of course, the training. Then why it's good, of course, it helps us to reduce the GPU memory usage. Then also it speeds up training because lower precision computations are faster. Then we have what we call weighted random sampler for class imbalance handling. So this one is a method to oversample the minority class. Since we have a large class imbalance, we use what we call the weighted random sampler for class to handle the class imbalance. So it prevents a model from being biased towards the majority class, where we do oversampling of the minority class and we do undersampling of the majority class. Then the hyperparameters of here, I used the batch size of 16. Of course, I trained a model using the two epochs. The learning rate was 0.003. The weight decay 0.001, and the loss function was, of course, calculated using the Focal laws, and the gamma was 2. As I said later on, the image sizes for the efficient net before, I used 380 by 380, then for the rest net, 224 by 224. Then the explainable AI. So the explainable AI technique, I use the GradCam. Its purpose is to visualize regions of image influencing predictions, then to generate heat maps highlighting the parasitic location. Unfortunately, I didn't visualize it, but I think I have to visualize this because the benefits it gives us, it improves the model interpretability. Then also it helps to verify biological relevant features. Of course, you view through the heat map and see how the correlation moves through between different classes. Then it also ensures the model to focus on the parasitic structures instead of the noise. So that is it. Where it's applied actually in audit predictions of both the architectures. That is the EfficientNet B4 and the ResNet 50. Then the results that we had, I had actually 1, 2, 4, 1 blood smear images. Of course, the overall class, the accuracy for the EfficientNet was 100%. Then for the net was 99%, as you see there. Then the Babesia F1 score was 1.01 actually net. Even equally for the ResNet was 1. Then for the leukocyte, F1 score was 1, 2, even for ResNet 1. Then there was a slight decrease in Plasmodium score, F1 score, where the EfficientNet slightly scored above the ResNet. As you're seeing, the value of the EfficientNet before was 0.98. Then for the other ResNet was 0.96. Then for the red blood cells, F1 score, all of them score the same, meaning they all perform outstandingly, perform perfectly in that. So basically the models, both models performed well on Babesia in the F1 score, in the Babesia, the leukocyte, and the RBC, and the rest were a bit slight changes, but I think more adjustments will come up to see that they both achieve maximum what? The maximum prediction that we want. Then the observations, of course, of the models trained, both models performed exceptionally well, though there was a slight decrease in some of the classes. For example, the Plasmodium detection was slightly better in the EfficientNet compared to the ResNet. Then the Babesia and the leukocyte detection, all the models had the perfect F1 scores for Babesia and leukocyte. Then even for the red blood cells classification, all of them had perfect and the other had near. So the overall model, it was the EfficientNet before slightly outperformed that, as seen by these results. So here is a confusion matrix visualization for both the models. Here I have the EfficientNet confusion matrix. Then on the right hand, I have the ResNet 50 confusion matrix visualization. So actually, the confusion matrix actually helps us to show the performance of the model in classifying these 4 class categories. So for example, of course, the 4 classes, we have the red blood cells, Plasmodium, we have also the leukocyte and Babesia. Then, of course, the rows show the actual class, then the columns represent the predicted class by the model. So let me start with the EfficientNet before confusion matrix. I seeing the diagonal values, the most predictions of this confusion matrix, they lie along the diagonal, meaning the model correctly classified most of the images. But of course, we had some classes were classified under Plasmodium. For example, when you check whether one red blood cell was classified under Babesia, which I see it were maybe some of these cells, maybe they resemble, that's why it was classified under there. Then also I'm seeing The 4 red blood cells were classified under Plasmodium, meaning there was a slight, a bit confusion there, whereby the model classified 4 red blood cells under Plasmodium. Then the rest, it was 0-0, meaning the model performed very well in detecting Plasmodium, Babesia, and leukocytes. That means there is some, and it did some slight mistakes in classifying red blood cells. Then on the other side of the ResNet confusion matrix, following the diagonal, the model correctly classified most of these images, but I see some errors in where it classified 2 Plasmodium cells as the red blood cells. So, and also I saw one red blood cell being classified into Plasmodium. But generally, the model performed well in other classes because it was able to detect all the Babesia, the leukocyte, the Plasmodium, and the RBC. So, particularly maybe basing on this, when you calculate our accuracy, it can be maybe, for example, for the efficient net, it can go to maybe 99 point something. Then basically for here, it can also maybe be at 98. So basically that is what I had for my models. So thank you for listening.